You know, there is something incredibly comforting about a physical server rack. Like if you've ever stood in a legacy data center, you know exactly what I mean.
Oh, absolutely. The deafening hum of the cooling fans. Right.
Right. And the tangled waterfall of Ethernet cables just cascading down the racks. Plus those thousands of little blinking green lights. It's just, well, if a database server goes down in that environment, you can physically walk across the raised floor, point a finger at the box with the red light and say, there is the problem.
Yeah, it's tangible. The hardware is right there in front of you. It gives you this profound, almost psychological sense of control. I mean, if a process runs out of control or if the network is compromised and all your software interventions fail.
You just pull the plug.
Exactly. You reach out, grab the heavy black power cable and pull it. It is a very binary, deeply physical relationship with your infrastructure. You literally own the metal.
But then, your organization decides to migrate to the cloud. You step into the world of AWS, and suddenly that physical server rack completely vanishes. You're operating in this highly abstract, invisible plane where hardware is like just a concept hidden behind an API call.
And that transition is jarring for a lot of people.
It really is. And what I find so endlessly fascinating and honestly a little terrifying is how engineers and systems administrators react to that sudden loss of physical control. I mean, they panic.
They absolutely panic.
Right. And because they panic, they instinctively try to recreate that physical control in the abstract cloud using their old habits. Welcome to today's deep dive, by the way. Today, we are completely immersing ourselves in the mind of an AWS Certified CloudOps Engineer.
Which is such a critical perspective to take. We're breaking down a massive stack of real-world architectural scenarios and exam discussions for the SOA-C03 certification.
Exactly. And our mission today isn't just about memorizing multiple choice answers. We are extracting the fundamental architectural why behind AWS best practices. So if you are prepping for the exam or gearing up for an architecture review, or you're just insanely curious about cloud operations, you have probably fallen into what we call the public forum hive mind.
Oh, the hive mind. That is a dangerous place to be.
It really is. It's this trap where engineers default to writing manual scripts or using legacy tools just because it feels familiar, rather than leveraging native cloud patterns. So we are going to dissect constraints like cost, security, and operational overhead to show why the obvious programmatic answer is actually, well, a trap.
Yeah, we're going to get into the native magic like systems manager, stack sets, SCPs, and event bridge.
Okay, let's unpack this. I want to start at the ground level, managing compute instances. Like we were saying, the most common pitfall for traditional sysadmins moving to the cloud is bringing their old tool belts with them.
Yeah, they pack up their custom shell scripts, their cron jobs, their manual SSH keys, and they just drag them into a brand new universe. They try to treat like a globally distributed, software-defined network exactly like a metal box sitting in a cold room in New Jersey.
Which is wild when you think about it.
It is, and that instinct is the absolute definition of technical debt. It's just a fundamental misunderstanding of the medium they are working in.
So imagine you are sitting at your desk, you just migrated your workloads, and you are staring at a fleet of, say, 100 Amazon EC2 Windows instances. The migration went well. The CloudWatch agent is deployed across the fleet. The servers are running. The application is serving traffic. Everything is great.
Until the security team knocks on your door.
Right. Suddenly, your security operations team drops a high-priority ticket in your queue. They have a new compliance mandate. You need to instantly start capturing the DHCP log files, the dynamic host configuration protocol logs that track IP address assignments. And you only need to pull these logs from exactly 50 specific instances out of that 100.
And if you go online right now to any public forum or message board and ask how to do this, the hive mind is going to give you a very specific type of answer.
Let me guess. Write a script.
Exactly. They will almost universally suggest manual intervention dressed up as automation. They'll tell you to open up your terminal, log into a jump box, and write a custom PowerShell script.
I mean, to be fair, the logic seems straightforward to them, right?
Sure. They think, okay, I'll create a loop in PowerShell, feed it a text file with 50 IP addresses, authenticate to each Windows machine using administrator credentials via WinRM, modify the local CloudWatch configuration file to track the DHCP path, and then just restart the service.
Okay, let me play devil's advocate here. Because if I am a traditional sysadmin, I am looking at that solution and thinking, hey, I know PowerShell inside and out. Writing a loop to iterate through 50 IP addresses and append a few lines of JSON to a text file will take me like 20 minutes to write and 5 minutes to run.
And the ticket gets closed before lunch.
Exactly. So why is everyone so terrified of a simple script? Why is that considered a trap?
Because you are only thinking about the optimal happy path execution of that script. You really have to consider the blast radius of failure and, well, the ongoing operational burden. When you write that PowerShell script, you've just given birth to a piece of custom proprietary software that your company now owns and has to maintain forever.
Oh, right. Like a pet.
Exactly like a pet. Let's trace the failure states. What happens if, precisely when you execute your script, 3 of those 50 instances are undergoing an automated reboot and are temporarily offline?
My script throws a connection timeout error.
Correct. And does your script have exponential backoff and retry logic built into it?
Definitely not. I wrote it in 20 minutes.
Right. So now your fleet is in an inconsistent state. 47 servers are compliant, 3 are not. You have to manually figure out which ones failed and rerun the script. But honestly, it gets worse. How are you handling the administrative credentials required to execute those remote commands on those 50 boxes?
Well, usually people just hard code them, which is terrible.
It's a massive security breach. If you hard code a password or a key into that script, and that script gets committed to a Git repository, you are in huge trouble. And if you try to pull the credentials dynamically from a secrets manager, well, you have suddenly turned a 20-minute script into a complex software engineering project.
Yeah, that makes sense. You're building this fragile, error-prone mechanism, opening remote execution ports, and juggling highly privileged credentials, all just to change a text file.
Precisely.
So we are essentially building a custom car engine out of spare junkyard parts just to drive to the grocery store when there's a free taxi waiting outside. But what is the alternative? Like, if I can't script it, how do I actually command the fleet?
You use the mechanism AWS built specifically for this exact problem, AWS Systems Manager, and specifically the run command feature.
Okay, run command. How does that avoid the credential problem?
To understand why this is superior, you have to look at the architecture of the Systems Manager agent, the SSM agent. This is a lightweight piece of software that is pre-installed on almost all modern Amazon machine images. It just runs as a background service on your instances.
But how does it receive commands if I'm not opening an inbound port like SSH or WinRM?
That is the brilliant part. It does not listen on an inbound port. The SSM agent constantly polls the Systems Manager endpoint in the AWS cloud via outbound HTTPS traffic on port 443. It's basically asking, do you have any work for me? Do you have any work for me?
Oh, wow. So it's a pull model, not a push model.
Exactly. When you want to capture those DHCP logs, you don't write a script. You go to Systems Manager, you select the 50 instances, likely by just pointing to a resource tag like environment, production web, and you issue a run command to update the CloudWatch configuration using the append config option.
And because it's pulling outbound, I never had to open a firewall. I never had to manage an administrator password.
It's 0 credentials. The authorization is handled entirely by the IAM instance profile, which is the identity attached directly to the EC2 instance itself, and Systems Manager handles the state. If an instance is offline, Systems Manager just queues the command and delivers it the moment the instance boots up and checks in.
That is so much cleaner.
It natively handles the logging of the command output, too, dropping the execution results directly into an S3 bucket or CloudWatch log, so you have this perfect auditable trail of exactly what happened on that server. You achieve complete compliance with 0 custom code and 0 exposed ports.
That shift in thinking from pushing commands via a script to having agents pull commands via a managed service is massive. But I want to push this architecture until it breaks. Let's scale it up.
Okay, let's do it.
Imagine a company running a critical business application across more than 300 Linux-based instances. They all have the SSM agent installed. They are all tagged. Now, a critical software package update is released, and it needs to be downloaded from the company's internal private repository and installed on all 300 machines immediately.
That sounds like a recipe for a bottleneck.
It is, because that private repository is hosted on an older, fragile server. If 300 instances suddenly hit it with download requests at the exact same millisecond, the repository's network interface will saturate, the server will crash, and literally nobody gets the update. So the constraint is strict. You cannot allow more than 30 simultaneous downloads at any given time.
This is a classic distributed systems concurrency problem, the thundering herd. And once again, engineers retreating to their comfort zones will suggest incredibly convoluted programmatic solutions.
Right, like if we abandon the jump box and try to be cloud native, I can see a developer saying, I'll write an AWS Lambda function in Python. It reads the list of 300 instance IDs. Then I will configure the Lambda function's reserved concurrency setting to 30. That way, AWS physically prevents more than 30 executions from happening at once.
It sounds incredibly sophisticated, right? It sounds sophisticated until you understand how Lambda reserved concurrency actually behaves under pressure. Reserved concurrency acts as a hard ceiling on active execution environments.
Okay.
So if a massive fan-out event triggers 300 Lambda invocations simultaneously and your limit is 30, Lambda does not politely queue the remaining 270 requests in a neat little waiting room. It actively throttles them. It drops them.
Wait, really? It just rejects the requests entirely?
Exactly. They fail with the too many requests exception. To make that Lambda architecture work, you'd have to introduce Amazon SQS, a queuing service. You'd push all 300 instance IDs into the queue. Then you configure Lambda to pull the queue. Then you have to write error handling in the Python code in case the package download fails on the Linux side.
This is getting complicated fast.
Oh, it gets worse. Then you have to configure a dead letter queue for the messages that fail repeatedly. You have just designed a distributed, asynchronous, multi-service architecture just to implement a speed limit.
Yeah, that is definitely technical debt. Another suggestion I often see for this is using AWS step functions. Like, you build a state machine with a parallel processing state, hard code the parallel branches to 30, and then just loop it 10 times until all 300 are done.
Which is financially and operationally disastrous. Step functions charge you based on the number of state transitions. You are paying for every single step of that loop. You're writing complex JSON state machine definitions. You're debugging visual execution graphs. It is an immense amount of operational overhead for a simple package update.
So we're back to Systems Manager. Does run command actually understand concurrency?
It understands it natively at the API level. You do not write any code. You issue the run command targeting the instances via their tag. But in that exact same API call, you just configure the max concurrency parameter. You simply set it to 30.
And that's it.
That's it. Systems Manager takes over the entire orchestration problem. It contacts the first 30 instances. As soon as instance number 4, for example, finishes its download, Systems Manager contacts instance 31. It dynamically manages the rolling execution across the fleet, guaranteeing that no more than 30 instances are ever active at once.
That is wild. It protects your fragile repository without you having to build a single queue or write a single line of error handling code.
Exactly. It's brilliant because you are offloading the heavy lifting of orchestration entirely to the AWS control plane. The underlying philosophy here is that AWS has already encountered and solved the orchestration problem for compute fleets. Anytime you find yourself writing a while loop to iterate through infrastructure, you need to stop and ask if a native service already does this.
And this philosophy becomes critically important during high-stress scenarios like emergency security patching. Let's look at a true nightmare scenario. A company has deployed custom Amazon Machine Images AMIs across hundreds of instances in 2 different AWS regions. It's Friday night, and a massive zero-day exploit drops for the underlying Linux operating system.
Oh, the dreaded Friday night 0 day.
Right. The security team declares an emergency. You don't even have an accurate inventory of how many instances are affected across the 2 regions. I have lived through the Friday night 0-day scramble. The sheer panic in the Slack channels is visceral. The instinct is to mobilize a team of engineers, distribute the SSH keys, divide up the IT ranges, and have everyone manually logging into boxes to run apt-get update or yum update.
Which introduces a secondary security crisis. Distributing highly privileged SSH keys to a dozen panicked engineers during an active incident is exactly how credentials get leaked, copied to personal laptops, or left behind on jump boxes.
But hold on, if we are truly embracing modern cloud architecture, shouldn't we refuse to patch entirely? Like, the doctrine of immutable infrastructure says we should never log in and modify a running server. We should just update the base AMI with the patch, terminate all the infected instances, and let the auto-scaling group spin up fresh, clean servers.
Okay, yes, the immutable infrastructure doctrine is fantastic for scheduled deployments and standard release cycles, but you have to match the response to the reality of the crisis.
Right. Time is of the essence.
Exactly. A zero-day exploit requires immediate mitigation. If you try to build a new AMI, push it through your testing pipeline, update your launch templates across 2 different geographic regions, and then orchestrate a rolling replacement of hundreds of instances without causing an application outage, you are looking at hours, possibly days, of work.
And during those hours, the vulnerability is actively exposed to the internet.
Yes. And consider this. What if that new AMI has a subtle bug in it that breaks the application upon boot? You have just caused a massive self-inflicted outage while trying to fix a security flaw.
That is the worst-case scenario.
You need a surgical, rapid response. And the native tool for this is AWS Systems Manager Patch Manager. Instead of scripts or AMI pipelines, you define a patch baseline.
What does the baseline actually do?
A baseline is simply a set of rules that says, for example, approve all critical security updates for Ubuntu automatically. You can execute a patch manager scan across both regions instantly to get a centralized dashboard showing exactly which instances are non-compliant. Then you simply execute a patch now operation.
And because it uses the SSM agent, it's doing it securely without SSH keys, pulling the packages, installing them, and reporting back the success state.
It rolls out the zero-day patch securely, concurrently, and with a full audit trail. It's the least operational overhead with the maximum speed.
So the lesson of the automation trap is pretty clear. Put down the shell scripts. Put down the complex orchestration pipelines for simple tasks. If you are managing the internal state, the configuration, or the software of a fleet of EC2 instances, your entire workflow should orbit around Systems Manager. But, this brings up a really critical limitation. Systems Manager is fantastic for tasks we initiate, like patching or deploying software. But what happens when things break on their own? Like, we can't schedule a fix for an unpredictable failure.
Right. And you're identifying the dividing line between automated operations and true self-healing architectures. In traditional IT, our approach to unexpected failures was entirely reactive and heavily reliant on polling.
Oh, the monitoring scripts.
Yes. You would write a monitoring script, a cron job that wakes up every 5 minutes, pings the server, and asks, are you healthy? Is the port open? Is the disk full? If the server fails to respond, the script sends an email to a human being who then has to log in and fix it.
I used to write those cron jobs. They are the backbone of legacy IT. Why is polling considered an anti-pattern in the cloud?
Because polling is inherently inefficient and dangerously slow. Let's say your cron job runs every 5 minutes. If a critical service crashes 10 seconds after the cron job finishes, your system sits completely broken in the dark for 4 minutes and 50 seconds before the monitoring tool even notices.
That's a huge blind spot.
It is. You are burning compute cycles 99% of the time, asking questions when everything is fine, and introducing massive delays the 1% of the time when everything is broken. In AWS, we shift from polling for state to reacting to events. When a resource changes state, it broadcasts a JSON payload and event instantly.
Let's ground this in a real scenario, because the difference between polling and event-driven reactions is profound. Imagine a company is running an FTP server hosted on an EC2 instance. They are using AWS Security Hub, which acts as a centralized security posture management service. Suddenly, a junior developer makes a catastrophic mistake in the AWS console.
Happens all the time.
They modify the security group attached to that FTP server and accidentally open port 21 to 0.0.000. They have just exposed the FTP port to the entire public internet. Security Hub immediately detects this policy violation and fires off an event to Amazon EventBridge. Our goal is to automate the remediation so no human ever has to get involved.
Now let's analyze how the legacy mindset tries to solve this within the cloud. The instinct might be to write a cron job running on a separate management server that constantly uses the AWS CLI to describe all security groups, loops through the rules, looks for that 0.0.00000 on port 21, and deletes it.
Which brings back the 5-minute window of vulnerability we just talked about. 5 minutes is an eternity for an automated botnet to find an open port and start brute forcing passwords.
It is entirely unacceptable from a security standpoint. Another option, which leverages EventBridge but completely misunderstands operational impact, is to configure the EventBridge event to trigger an action that simply stops the EC2 instance entirely.
I have actually seen people do this. They argue, hey, it solves the security problem instantly. The server is powered off, the port isn't exposed.
It solves the security problem by intentionally causing an availability problem. You have just taken a production application offline because of a misconfigured firewall rule. It is a completely disproportionate response. The elegant, event-driven approach is surgical. You configure EventBridge to catch the specific JSON event emitted by Security Hub. The target of that EventBridge rule is an AWS Lambda function.
Okay, so the Lambda function receives the event data containing the exact ID of the compromised security group.
Exactly. The Lambda function does not touch the EC2 instance. It does not reboot anything. It simply takes the security group ID, makes a rapid API call to the Amazon VPC service, specifically the revoke security group ingress API, and strips out that single offending rule.
Wow, that is clean.
The server stays online, business operations continue uninterrupted, and the security hole is closed in milliseconds, long before any human even reads the alert.
EventBridge essentially acts as the central nervous system of the AWS environment. A nerve ending senses pain, fires a signal to the brain, and the brain instantly jerks your hand away from the hot stove. But sometimes you don't even need to write the Lambda function yourself, do you? Because AWS has already anticipated these common mistakes.
This is a major area where engineers over-engineer their solutions. Let's look at another common violation. A developer is trying to debug a connection issue, gets frustrated, and manually opens SSH port 22 to the world on a production web server. The company is using AWS Config, a service that continuously monitors and records the configuration state of your resources. AWS Config instantly flags the resource as non-compliant because it violates a managed rule checking for open SSH ports.
So following our previous logic, I take the AWS config event, route it to EventBridge, write a custom Python Lambda function that calls the revoke security group ingress API for port 22 and attach it to the rule. That works, right?
It works perfectly, but it is not the most operationally efficient way. And in architectural discussions, efficiency is everything. When you write custom Python code, you have to maintain it. You have to update the runtime when Python versions deprecate. AWS Config actually has automatic remediation actions built directly into the service.
Oh, really?
Yeah, there is a native AWS managed remediation runbook literally called AWS Disable Incoming SS Shown Port 22.
Wait, they have a runbook specifically for that exact mistake?
Yes. You simply attach that native systems manager automation runbook to the AWS config rule. The moment config detects the violation, it executes the runbook natively. It handles the API calls securely in the background. No EventBridge wiring required, no custom Lambda code to write, no runtime deprecation warnings to worry about. You are using the platform's native immune system.
That is a massive paradigm shift. Before you write a single line of custom remediation code, your first step must be to search the AWS Systems Manager Automation Document Library. There is a very high probability that an AWS engineer has already written, tested, and maintained the exact remediation logic you are about to build.
Exactly. Don't reinvent the wheel.
Let's look at another scenario that highlights the shift away from cron jobs, but this time focused on scheduling rather than security. A company's marketing department has a business requirement. They need to send a specific automated notification to millions of subscribers every single Saturday at 8:00 a.m. They are already using Amazon Simple Notification Service, SNS, to distribute the messages, but currently, an intern is literally logging into the console and pushing the publish button manually every Saturday morning.
If you ask a legacy systems administrator to automate this, they will rely on the only tool they know, a server. They will provision a tiny t3.micro EC2 instance. They will write a bash script utilizing the AWS CLI to publish the message to the SNS topic. Then they will configure a cron job on that Linux machine to execute the script every Saturday at 8 a.m.
And what is the true cost of that solution?
The true cost is staggering inefficiency. You are paying for an EC2 instance to sit completely idle, burning electricity and budget for 167 hours and 59 minutes a week just to run a script for 1 second on Saturday.
That's hilarious when you frame it like that.
And furthermore, that instance now exists in your environment. It needs an operating system. That OS needs to be patched. The instance needs a security group. It needs IAM credentials. It needs disk space monitoring. You have introduced an entire layer of operational overhead just to act as an alarm clock.
I see engineers trying to solve this serverless style by using AWS step functions. They build a state machine with a wait state that just pauses execution until Saturday and then triggers an SNS publish task.
Step Functions is an incredible service, but it is designed as an orchestration engine for complex, multi-step, long-running workflows like order processing or video encoding. Using a complex state machine just to trigger a single isolated SNS message on a fixed schedule is using a supercomputer to do long division. The most elegant, operationally efficient, and cost-effective solution is EventBridge.
How does EventBridge handle scheduling without an event triggering it?
EventBridge has a feature called Scheduled Rules. You literally just input a standard cron expression specifying 8:00 a.m. on Saturdays. You set the target of that rule directly to the Amazon SNS topic. You construct the JSON payload you want to send in the rule definition, and that is it.
No servers, no Lambda functions acting as middlemen, no state machines.
Nothing. It is a serverless rule, natively invoking a serverless notification service. The infrastructure scales to zero when it's not running. You are paying fractions of a cent per month, and there is absolutely nothing to patch or maintain.
Let's tackle one more event-driven scenario, because this specific telemetry problem trips up so many engineers. We have an application running on EC2, and due to a known bug in a legacy library, occasionally an errant process gets stuck in an infinite loop and spikes the server CPU to 100%. The engineering team is working on a permanent code fix, but in the meantime, the business requirement is strict. If the CPU stays at 100% for more than 2 minutes, the server must be automatically rebooted to clear the stuck process.
This is a phenomenal scenario because it tests your deep understanding of how telemetry actually functions in the cloud. The instinctive approach is to think about Lambda again. I will create a CloudWatch alarm that monitors CPU. If it hits 100%, it triggers a Lambda function that calls the EC2 Reboot Instances API.
But based on everything we've discussed, I know that writing custom API code when a native feature exists is wrong. CloudWatch alarms have EC2 actions built right into them, correct?
Yep. Yes. You can configure a CloudWatch alarm to directly terminate, stop, or reboot an instance without any intermediate Lambda function. But the trap in the scenario is not the action, it is the timing constraint. The prompt specifically demands a reaction if the CPU is maxed out for more than 2 minutes.
Let's look at the frame rate of our monitoring. By default, standard Amazon EC2 basic monitoring only aggregates and delivers metric data points to CloudWatch every 5 minutes.
Exactly. It's like watching a security camera that only takes one photograph every 5 minutes. If a thief breaks in, steals the safe, and leaves within 4 minutes, the camera completely misses it. If you build your CloudWatch alarm based on standard 5-minute basic monitoring, it is physically impossible to meet a 2-minute self-healing service level agreement. The alarm won't even know the CPU spiked until 5 minutes have passed.
So how do we increase the frame rate?
You must enable detailed monitoring on the EC2 instance. Detailed monitoring alters the telemetry agent to collect and publish data points at 1-minute intervals. Once detailed monitoring is enabled, you can configure your CloudWatch alarm to evaluate the CPU metric over 2 consecutive 1-minute periods. If both periods read 100%, the native EC2 reboot action fires.
So the architectural lesson is that your visibility dictates your reaction time. You cannot build a rapid response automated system if your telemetry is lagging.
And critically, that visibility comes with a financial cost. Basic monitoring is free. Detailed monitoring is a paid feature per metric. The CloudOps engineer must weigh the financial cost of detailed telemetry against the business cost of a server sitting frozen for 5 minutes.
Okay, let's zoom out. We have been deep in the weeds. We have talked about fixing single instances with Systems Manager, and we've built event-driven rules to surgically remove bad security groups or reboot frozen servers. But fixing a bad security group rule after it is deployed, even if it's fixed in milliseconds by EventBridge, is still a reactive posture. The bad rule existed. The vulnerability was live, however briefly. What if we could prevent the bad architecture from being deployed in the first place? And what if we have to enforce these rules not just in one single VPC, but across a massive global enterprise with 200 distinct AWS accounts?
Now we are entering the realm of multi-account governance and guardrails. For an associate-level engineer looking to transition to a senior architect role, this is the most critical mindset shift you can make. You must stop thinking about how to build a specific resource and start thinking about how to mathematically govern the entire environment where resources are built.
The foundational service for operating at this scale is AWS organizations. When a company reaches enterprise scale, they do not shove everything into one giant AWS account. The blast radius would be terrifying. Instead, they have dozens, sometimes hundreds, of distinct member accounts, and they group them logically into organizational units, or OUS.
Let's examine a scenario that illustrates the power of this structure perfectly. An enterprise has an organizational unit called the Application OU, which contains 30 different AWS accounts used by various development teams. The CloudOps engineer is handed a strict mandate from the finance department to prevent any user from launching any Amazon EC2 instances into any account within this Application OU, unless the instance is explicitly tagged with a key called Cost Center Project. If it doesn't have the tag, the launch must fail, and this restriction must only apply to this specific OU.
Okay, I am going to put on my hive mind hat again. If I am tasked with restricting user permissions, my brain immediately goes to AWS Identity and Access Management, IAM. I know how to write an IAM policy. I would write a policy that says, allow the EC2 run instances action, but only with a condition key that mandates the presence of the Cost Center Project tag. Then I just attach that IAM policy to every developer, administrator, and CI/CD role across all 30 accounts.
And how exactly do you manage the life cycle of those policies across 30 accounts as the company dynamically scales? What happens when a new engineering team is onboarded and someone simply forgets to attach that specific conditional policy to their new IAM roles?
Right? Human error.
Exactly. What happens if a senior administrator who naturally possesses administrator access policies logs into troubleshoot and provisions an untagged instance to test something? Your decentralized IAM approach relies entirely on perfect, ongoing, manual human management. And in operations, any security posture that relies on humans never making a mistake has already failed.
Okay, I see the flaw. IAM policies control what a specific identity is allowed to do. But if they have multiple policies, the permissions can stack, or an admin policy can override my restrictive policy. What is the mechanism for absolute top-down enforcement?
The mechanism is a service control policy, or an SCP. An SCP is a radically different concept than an IAM policy. An SCP does not grant permissions to anyone. You cannot use an SCP to allow a user to do something. Instead, an SCP defines the absolute maximum available permissions for an entire AWS account or an entire organizational unit. It acts as an impenetrable mathematical guardrail.
Think of it like taking a child to a bowling alley. An IAM policy is like the specific bowling ball you hand to a person. You give a child a light 6-pound ball so they can throw it. You give a professional bowler a heavy, custom-drilled reactive resin ball. They have different capabilities. But an SCP is the metal bumpers you inflate in the gutters. It does not matter what ball they use. It does not matter if it's a child or a professional throwing it with all their strength. If the bumpers are up, that ball is staying in the lane, period.
That is a highly accurate way to visualize it. To solve the tagging problem, you author an SCP that explicitly denies the EC2 or instance's action when the cost center project tag is missing. You do not attach this to users. You attach this SCP to the application OU itself.
And what happens then?
The moment you do that, the guardrail descends across all 30 accounts simultaneously. It does not matter if a user logs in with full administrator access in their local IAM policy. When they try to launch an untagged instance, the AWS authorization engine evaluates the request. It sees the IAM allow, but then it checks the SCP. Because the SCP has an explicit deny, the action is blocked. The local administrator is completely overridden by the organizational guardrail.
That is immense power. It completely centralizes governance. Let's look at a more aggressive scenario from the sources. A company has suffered a security breach because someone logged in using the root user credentials of a member account. The mandate is to completely block root user actions in all 200 member accounts across the entire enterprise and simultaneously prevent anyone, even local account admins, from disabling or deleting AWS CloudTrail logs.
Again, if you try to solve this locally with IAM, you lose. A local administrator can just modify their own IAM policy to give themselves permission to delete CloudTrail, or they can just log in as root, which inherently bypasses IAM restrictions.
So go back to SCPs.
Yes. You must utilize AWS organizations, and ideally AWS Control Tower, to deploy SCPs at the root level of the organization. You create an SCP that explicitly denies all actions if the AWS. Principal type is account, which signifies the root user. And you deny all CloudTrail, stop logging, and CloudTrail delete trail actions. Applied globally, the enterprise is instantly hardened against these actions.
What if the restriction isn't about an action, but an entire service? Say, for strict regulatory compliance, a healthcare company mandates that absolutely no one is allowed to use Amazon DynamoDB anywhere in the organization because it hasn't been approved by the internal audit board.
The anti-pattern is writing a script to crawl through hundreds of accounts, trying to identify and delete any DynamoDB tables, and constantly updating IAM policies to prevent new ones. The elegant centralized solution is to author a single SCP in the management account that simply says, affect, deny, action, dynamod, resource.
Wow, just like that.
Yep, apply that SCP to the organization root. In 1 second, with 20 lines of JSON, DynamoDB is mathematically disabled across 200 accounts, regardless of local permissions.
So SCPs are the ultimate defense for security and compliance guardrails. But governance isn't just about blocking things. It's also about building things consistently. What about deploying actual baseline infrastructure across all those accounts? We have a scenario where a CloudOps engineer has crafted a complex AWS CloudFormation template that deploys standard VPCs and security groups. And they need to roll this exact template out to 40 different member accounts.
The scripting instinct strikes again here. The hive mind will tell you to write a Python script using the Bodo 3 SDK. The logic goes like this. The script uses the AWS Security Token Service, STS, to call the assume role API to assume an administrative role in account 1. It deploys the CloudFormation stack, then it assumes a role in account 2, deploys the stack, and so on.
I can feel the fragility of that script just hearing you describe it. You are writing a massive loop that has to handle network timeouts, STS token expirations, and cross-account IAM trust policy management. If the script fails on account 28, how do you cleanly resume it? It's a fast track to burnout.
It is entirely unnecessary, undifferentiated heavy lifting. The native AWS pattern designed specifically for this problem is AWS CloudFormation stack sets. A stack set extends the functionality of standard CloudFormation. It allows you to create, update, or delete stacks across multiple AWS accounts and multiple AWS regions with a single operation. You deploy the stack set centrally from the management account or a delegated administrator account.
And AWS handles the underlying orchestration.
AWS natively handles the cross-account role assumption, the parallel deployments across regions, and the failure handling. You just tell the stack set, deploy this template to the application OU, and AWS reliably distributes the infrastructure.
Okay, we've put the bumpers in the gutters with SCPs. We've automated the deployment of the pins with stack sets. We've enforced tagging so we know exactly who is paying for the lane. Actually, let's pause on tagging, because there is a very subtle cost allocation gotcha that trips up a lot of people. In one of our scenarios, a company successfully uses an SCP to enforce that every single resource is tagged with cost center project. They deploy resources for 20 days. Then, the finance team logs into the AWS Cost Explorer console to generate a billing report broken down by cost center. But they can't. The tag doesn't exist in the billing dashboard as a filter option. Why?
Because merely tagging a resource at the infrastructure level does not automatically inject that tag into the billing and analytics engine.
Why not? Why isn't it automatic?
Because of the sheer volume of data. Across millions of AWS customers, there are billions of arbitrary user-defined tags created every day. Dev, test, Bob's experiment, temp, delete later. If the AWS billing engine indexed every single arbitrary tag into its multidimensional cost analytics database by default, the system would collapse under the weight of useless metadata. You have to explicitly tell the billing engine which tags carry financial meaning.
So how does the CloudOps engineer fix the finance team's problem?
They must navigate to the AWS Billing and Cost Management console, go to the Cost Allocation Tag section, locate the user-defined Cost Center project tag, and explicitly activate it. Once activated, the billing engine begins indexing that specific key. It usually takes up to 24 hours for the tags to begin populating in Cost Explorer, and crucially, it is not retroactive. Those first 20 days of billing data will remain untagged in the dashboard.
That is such a critical, real-world operational detail. All right, let's shift gears. Our backend infrastructure is now flawlessly governed, consistently tagged, and automatically deployed. But none of this beautiful architecture matters in the slightest if the end customer, sitting at their laptop halfway across the world, cannot reach the application reliably. This brings us to the intricate world of networking nuances and the global user experience. Let's talk about the physics of traffic and routing.
Networking choices in cloud architecture are rarely just technical decisions. They are directly tied to financial outcomes. Uptime, latency, and packet loss directly impact revenue. If an e-commerce user adds an item to their cart and the next page takes 3 seconds to load because of inefficient routing, a measurable percentage of those users will abandon the cart. Your routing algorithms dictate your bottom line.
Let's start with a classic migration headache. A company executes a lift and shift migration, moving a legacy monolithic application from their on-premises data center into AWS. They deploy the application onto EC2 instances across multiple availability zones for redundancy, and they place an application load balancer, an ALB, in front of the fleet. Because it's a legacy application, it manages user sessions poorly, so it requires session affinity. A user must continuously route to the exact same backend server for the duration of their session. But shortly after going live, users began reporting random, intermittent application timeouts and 500-level errors. The operations team checks the ALB target group, and all the EC2 instances are reporting as 100% healthy. The legacy app never threw these errors in the old data center. What is fundamentally breaking down here?
To diagnose this, you have to understand the default mechanics of how an application load balancer distributes traffic. By default, an ALB uses the round-robin routing algorithm. It operates like a dealer handing out cards in a poker game. Request 1 goes to server A, request 2 goes to server B, request 3 goes to server C, request 4 goes back to server A. It blindly distributes the requests evenly across all healthy targets.
And why is that a problem for a legacy session-heavy application?
Because legacy applications often process requests at highly variable speeds. Imagine server A receives a complex request that requires a heavy database query. It might take 3 seconds to resolve. Server B receives a simple static image request that resolves in 10 milliseconds. If the ALB blindly uses round robin, it might deal 3 more complex, heavy requests to server A while it is still choking on the first one. Because the application requires session affinity, the connections queue up, the server's thread pool exhausts, and the user experiences a timeout.
And the health check.
The simple health check ping still registers the server as alive, but at the application layer, it is completely overwhelmed.
So how do we restructure the routing without having to rewrite the legacy application's codebase?
You modify the routing algorithm on the ALB target group. You switch it from round robin to the least outstanding requests algorithm.
How does that change the physics of the distribution?
Instead of dealing blindly, the ALB becomes acutely aware of the state of the backend connections. When a new request arrives, the ALB looks at the target group and evaluates how many active processing requests are currently open on each server. It might see that server A has 15 outstanding requests while server B only has 2. It will intelligently route the new request to server B. It dynamically smooths out the load, preventing any single legacy server from getting crushed, maintaining session stability, and eliminating the random application timeouts.
That is a phenomenal layer of intelligence. But let's drop down the OSI model, from layer 7 to layer 4, because sometimes intelligence is the enemy of raw speed. Let's look at an extreme scenario. An architecture is being designed to support a massive mobile gaming event. The application must scale from 0 to millions of requests per second almost instantaneously. The traffic is highly volatile with massive sudden spikes. And due to strict firewall rules on the client side, the architecture has an inflexible constraint. The load balancer must provide exactly one static IP address for each availability zone.
If an engineer isn't thinking critically, they reach for the application load balancer by default, simply because they use it for everything else. But an ALB completely shatters under both of those strict constraints.
Why does an ALB fail under a massive sudden spike?
Because of how it operates at layer 7 of the OSI model. When a client connects to an ALB, the ALB doesn't just pass the network packets through. It actively terminates the TCP connection. If it's HTTPS, it negotiates the SSL handshake and decrypts the traffic. It opens the HTTP payload, inspects the headers to see if it needs to route based on path or host, and then initiates a brand new TCP connection to the backend server.
It is essentially acting as a middleman, reading every single letter before passing it along.
Precisely. And that inspection requires compute power. Under normal scaling, the ALB dynamically provisions more underlying compute nodes to handle the load. But if you hit it with millions of requests in a single second, it does not have time to scale. It gets crushed. You have to engage AWS support to pre-warm the ALB, which is a manual, cumbersome process. Furthermore, because the ALB is constantly scaling its underlying nodes, its IP addresses are highly dynamic. It cannot provide a single static IP address per availability zone. It relies on DNS to resolve to its changing IPs.
So the ALB fails the speed test and fails the static IP constraint. What is the architectural solution?
You must architect using a network load balancer, or NLB. An NLB operates entirely at layer 4, the transport layer. It routes traffic based strictly on IP protocol data, like TCP or UDP ports.
So it doesn't terminate the connection or read the HTTP headers?
No. It alters the network packets on the fly and forwards them directly to the backend targets. Because it is not inspecting the payload or decrypting traffic, the computational overhead is virtually zero. It is incredibly fast and can natively absorb highly volatile spikes of millions of requests per second without requiring any manual pre-warming. And, critically for the constraint, an NLB inherently provides exactly one static IP address per availability zone, which you can even replace with your own custom elastic IP if your architecture demands it.
It is entirely about matching the tool to the specific physics of the traffic. Now, let's expand the scope geographically. We have an application hosted entirely in the US East 1 region in Virginia. It sits behind a load balancer. The company launches a massive global marketing campaign, and suddenly they have users connecting from Tokyo, Sydney, and Berlin. But the global users are flooding the support desk with complaints. They are experiencing severe latency, high jitter, and inconsistent performance. How do we fix global network physics?
The brute force architectural approach, which the exam will often tempt you with, is to embrace a multi-region active deployment. The suggestion is to copy your entire infrastructure, the web servers, the application tier, the databases, and deploy it into AWS regions in Japan, Australia, and Europe, and then use Route 53 latency-based routing to direct users to their closest region.
Which fundamentally changes the entire nature of the company's architecture. You are now paying for 4 times the compute. You have to manage complex multi-region database replication. You have to orchestrate deployments across the globe. The cost and operational overhead would be astronomical.
It is a massive overreaction if the application doesn't strictly require multi-region data residency. The elegant native solution to drastically improve global latency for a centralized application is to deploy AWS Global Accelerator.
I've always viewed Global Accelerator as a bit of black magic. How does it fundamentally alter the network path?
To understand the magic, you have to understand how the public internet routes traffic without it. If a user in Tokyo types in your URL, their request leaves their device, hits their local internet service provider, and then begins a long, unpredictable journey across the public internet. It hops from router to router, crossing various Tier 1 networks, submarine cables, and peering points all the way to Virginia. At every single hop, there is a risk of network congestion, packet loss, or suboptimal routing choices governed by the Border Gateway Protocol, BGP.
It's like trying to drive across a country using only back roads during rush hour. You will eventually get there, but it's going to be slow and unpredictable.
Exactly. When you provision AWS Global Accelerator in front of your Virginia load balancer, AWS provisions 2 static Anycast IP addresses for your application. Anycast is a routing methodology where the exact same IP address is broadcast from multiple geographic locations simultaneously.
So when the user in Tokyo connects to that IP,
the BGP routing protocols of the internet automatically direct their traffic to the topologically closest broadcasting node. In this case, the traffic hits an AWS edge location physically located in Tokyo.
they only travel over the public internet for a few miles.
Correct. The moment their packet hits that edge location in Tokyo, it enters the AWS Global Network backbone. This is a private, highly optimized, redundant fiber optic network owned and controlled entirely by AWS. The packet travels at the speed of light over a pristine, uncongested network directly to the East-East-1 region. Global Accelerator slashes latency, eliminates internet weather and jitter, and provides a drastically more consistent user experience without requiring you to deploy a single EC2 instance outside of Virginia.
Okay, we have optimized the global route, but how do we actually know the user experience is good? Let's look at an observability constraint. A company wants to monitor their critical website's uptime and receive an alert if it drops below 99%. But the prompt explicitly states a crucial constraint. The monitoring must provide an accurate view of the user experience.
This constraint demands a profound shift in how we think about telemetry and observability. Historically, systems administrators relied almost exclusively on server-side logs. The legacy approach would be to parse the application load balancer access logs and create a CloudWatch alarm that triggers if the count of HTTP 5XX server error spikes. If the server throws a 500, trigger the pager.
Why does that fail the constraint? Why isn't a server-side error log an accurate reflection of the user experience?
Because a server-side log only records the reality that the server actually observed. What happens if the customer's ISP fails to resolve the DNS record? What happens if the SSL certificate on your load balancer unexpectedly expires and the user's browser outright rejects the connection? What if a front-end developer pushed a broken JavaScript file and the application page renders as a completely blank white screen on the client's device?
The server never even receives a valid HTTP request in those scenarios.
Exactly. Because the request never reaches the application logic, the server never logs a 500 error. The server's internal metrics report that uptime is a flawless 100%, CPU is low, and everything is perfectly healthy, while out in the real world, thousands of users are staring at a broken web page. You are completely blind to the client-side failure.
So how do we architect observability from the outside in? How do we monitor what the customer actually sees?
You utilize Amazon CloudWatch synthetics. Specifically, you create a heartbeat monitoring canary. A canary is essentially a managed AWS Lambda function running a headless web browser, usually using Puppeteer or Selenium frameworks. It operates externally, acting exactly like a real user.
So it actually executes the entire life cycle of a request.
Yes. On a scheduled interval, the canary reaches out over the internet. It resolves the DNS, it negotiates the SSL handshake, it loads the DOM, it executes the JavaScript. It can even be programmed to click buttons or log in. It monitors the application from the outside, validating the entire chain of delivery. You then create a CloudWatch alarm based on the canary's success percent metric. If the canary fails to load the page, you know definitively that the user experience is broken, regardless of how pristine your server logs claim to be.
I love that philosophy. Don't trust the server to tell you if the server is working. Ask the customer. Or in this case, ask the robotic canary. Let's cover one final networking nuance, because this is a classic hybrid cloud headache that causes endless operational pain. A company has an on-premises data center securely connected to their AWS VPC via a dedicated AWS Direct Connect fiber link. The EC2 instances running inside the AWS VPC need to resolve the internal proprietary DNS names of legacy databases sitting back in the on-premises data center, say database.corp.local.
The manual, agonizing way to solve this, which unfortunately is a trap answer on the exam, is to constantly manage host files. An engineer might suggest writing a script to update the echoes file on every single EC2 instance with the static IP addresses of the on-premises servers. Alternatively, they might suggest manually maintaining a Route 53 private hosted zone within AWS and duplicating all the DNS records from the on-premises environment.
Both of those solutions require endless manual synchronization. If an on-premises server changes its IP address, the entire AWS environment loses connectivity until someone manually updates the AWS side. What is the native mechanism to bridge this DNS divide seamlessly?
The native solution is Amazon Route 53 Resolver. Specifically, you provision Route 53 Resolver outbound endpoints inside your VPC. These are managed elastic network interfaces that act as DNS proxies. Once provisioned, you configure a Route 53 forwarding rule. The logic of the rule is simple. Anytime an EC2 instance asks to resolve a DNS query ending in .corp.local, do not attempt to resolve it here. Forward that specific query through the outbound endpoints across the direct connect line directly to the IP address of the legacy DNS server sitting in the on-premises data center.
So the EC2 instance asks AWS. AWS forwards the question to the on-prem data center, gets the answer, and passes back. It is seamless, native, and completely eliminates the need to manually synchronize internal DNS records. Okay, let's take a breath and look at what we have built. We have engineered a fortress. We have event-driven, self-healing compute. We have impenetrable organization-wide SCP guardrails. We have highly optimized Layer 4 and Layer 7 routing, global network acceleration, and sophisticated outside-in observability. Our application is resilient, fast, and highly available.
It sounds perfect.
But here's the terrifying, unavoidable truth of cloud computing. Compute and networking are inherently stateless and ephemeral. If an EC2 instance crashes, autoscaling provisions a new one. If an ALB fails, AWS spins up another. But what happens when our stateful data, our customer databases, our compliance backups, our object storage is compromised, accidentally deleted, or maliciously corrupted?
That brings us to the final and most critical phase of architecture, data persistence, disaster recovery, and the immutable cloud. If you lose an instance, you experience a blip. If you lose the data, you lose the company.
Let's start with the ultimate nightmare scenario: malicious deletion of critical compliance data. A highly regulated financial company is storing financial audit backups in an Amazon S3 bucket. They are bound by a strict legal compliance requirement that states these backups must not be altered or deleted by anyone for a minimum of 3 months. No exceptions, no leeway.
The reflexive thought for an engineer who only understands access control is to rely on IAM. They will confidently state, I will just configure an IAM resource policy on the S3 bucket that explicitly denies the S3 delete object action for all users and all roles.
But IAM is just a software configuration. If a sophisticated attacker manages to phish or compromise the credentials of a senior cloud administrator, what stops them from just modifying that IAM policy?
Nothing. IAM is a locked gate, but an administrator inherently holds the master key to that gate. They can detach the policy, delete the data, and cover their tracks. To meet a strict, legally binding, immutable compliance requirement, IAM is fundamentally insufficient. You must implement protection at the storage layer itself. You must use S3 object lock. And specifically for the exam and real-world compliance, you must understand the deep mechanical difference between governance mode and compliance mode.
Let's unpack that. What is the operational difference between the two?
In governance mode, you are protecting data against accidental deletion by standard users or automated scripts. Users cannot overwrite or delete an object version during the retention period unless they possess a special, highly privileged IAM permission called S3 by bypass governance retention.
So governance mode still has a master key. An admin with that permission can still delete the data.
Correct. Governance mode fails the strict legal constraint of our scenario. To satisfy the mandate, you must utilize compliance mode. In S3 object lock compliance mode, the immutability is absolute. Once an object is written and the 3-month retention period is applied, that object version cannot be overwritten, modified, or deleted by any user. Not by an administrator, not by the root user of the AWS account, not even by AWS support engineers.
You are literally locking the vault and destroying the key for 90 days. The data is mathematically guaranteed to survive, completely impervious to compromised credentials or malicious insiders.
It creates a true worm environment. Write once, read many. It shifts the protection from identity-based access control to immutable physical storage physics.
Let's talk about a different kind of data disaster internal corruption. An application relies on a massive Amazon Aurora MySQL database. A junior developer is running a maintenance script, makes a typo in a SQL query, and accidentally executes a drop table command on the live production database. 2 hours pass before the application starts throwing massive errors and you get the frantic phone call. You need to recover the lost table data. But the architectural constraint in this scenario is incredibly specific. The data restore must be completed in the same production DB cluster.
This is a phenomenal example of how reading the constraints carefully dictates the architectural mechanism. If that constraint in the same cluster did not exist, the standard operational response would be point-in-time recovery or PITR.
Explain how PITR actually works under the hood.
Amazon Aurora continuously backs up your transaction logs to Amazon S3 in real time. If you initiate a point-in-time recovery, you specify the exact second you want to restore to, say, 5 seconds before the developer dropped the table. AWS pulls the base snapshot from S3, replays the transaction logs up to that exact millisecond, and provisions a brand new Aurora cluster.
A new cluster means a new database endpoint URL.
Exactly. And that implies significant downtime. You have to wait for the new cluster to provision, and then you have to coordinate a complex update of your application's connection strings, secrets manager, and DNS records to point the live application to the new cluster. But our constraint strictly forbids this. We must restore the data into the existing same cluster.
So how do we roll back time without building a new machine?
You leverage a feature unique to Aurora MySQL called Aurora Backtrack. To understand why Backtrack is the only answer, you have to understand Aurora's log-structured storage engine. In a traditional database, data is stored in physical pages, and when you overwrite it, it's gone. Aurora doesn't overwrite data in place. It writes a continuous stream of log records across a distributed storage volume.
So the historical states of the database naturally exist in the storage layer.
Precisely. Aurora Backtrack exploits this architecture. It does not rely on restoring massive amounts of data from S3. Instead, it literally just moves a pointer backward in the log sequence. You specify the time right before the table was dropped, and you execute a backtrack. In seconds, Aurora rewinds the cluster in place, instantly undoing the destructive transactions, up to 72 hours in the past.
The database endpoint remains exactly the same. The application doesn't even know anything changed. It is the closest thing to a magical undo button for a production database. Now let's scale the disaster up to the absolute maximum. We aren't just talking about a drop table. We are talking about losing a physical data center. We have a globally distributed financial application running its primary critical workload in US East 1 in Virginia. The business stakeholders have defined catastrophic disaster recovery constraints. They require a recovery time objective, an RTO, of less than 10 minutes, and they require a recovery point objective, an RPO, of strictly 0.
Let's clearly define those metrics because they govern the entire physics of the architecture. RTO recovery time objective is how long the business can afford to be completely offline before massive financial damage occurs. 10 minutes is incredibly fast. RPO recovery point objective is how much historical data the business can afford to lose during a catastrophic failure. A 0 RPO is the most demanding constraint in cloud architecture. It means if Virginia is hit by a meteor, absolutely 0 transactions can be lost.
Let's evaluate the standard disaster recovery strategies against these brutal constraints. The cheapest, most common strategy is backup and restore.
In Backup and Restore, you simply copy your database snapshots and AMIs to a secondary region, like Oregon. If Virginia goes down, you manually launch new EC2 instances in Oregon and restore the database from the snapshot. Your RTO would be measured in hours or days, and your RPO would be however old that last snapshot was. It fails the constraints entirely.
The next step up the cost curve is the pilot light strategy.
In a pilot-light architecture, you continuously replicate your database to the secondary region, but your web and application servers are turned off to save money. If disaster strikes, you start the application servers and flip the DNS. Your RPO is better because data is replicating, but booting up an entire fleet of application servers, warming them up, and shifting traffic will almost certainly exceed the strict 10-minute RTO constraint.
What about warm standby?
Warm standby means the application servers in the secondary region are actually running, but scaled down to a bare minimum capacity. It could potentially meet the 10-minute RTO as auto-scaling groups expand. However, ensuring an absolute zero data loss RPO 0 during a chaotic failover event usually requires highly active, synchronous or near-synchronous replication that a passive warm standby database might struggle to guarantee without manual verification or complex conflict resolution. To mathematically guarantee millisecond failover with absolutely zero data loss, you are forced into the most extreme architecture active.
Active means the application is running at full 100% production capacity in both Virginia and Oregon simultaneously, and real user traffic is being continuously routed to both regions.
Exactly. You utilize technologies like Amazon DynamoDB Global Tables or Amazon Aurora Global Databases for real-time multi-master data replication. You place Amazon Route 53 in front of everything, utilizing sophisticated health checks and latency-based routing to distribute the global user traffic. If the entire US East 1 region goes dark, Route 53 detects the health check failure in seconds and instantly shifts 100% of the traffic to the Oregon region.
Because Oregon is already active, the server's already warm, and the data is already synchronized, your RTO is essentially 0 seconds and your RPO is 0. So active architecture provides the ultimate holy grail of zero downtime and zero data loss. Why doesn't every single company just build active for every application?
Because the friction is immense. It is phenomenally expensive and architecturally agonizing. You are paying for double the compute infrastructure, double the load balancers, and massive cross-region data transfer costs. But more importantly, you have to re-architect your application code base to handle the complexities of distributed systems like multi-master database write conflicts, replication lag, and eventual consistency. Architecture is fundamentally the art of compromise between budget and availability. AWS provides the tools to survive a literal nuclear strike on a data center, but the business has to be willing to pay the premium to live in that bunker.
Which brings us perfectly to a very specific operational constraint around costs. This is a classic architectural gotcha that tests your deep understanding of how managed services are intertwined. A CloudOps engineer gets an alert from finance that their AWS bill is too high. The engineer decides to cut costs by completely disabling the automated backups on a massive Amazon RDS database instance, reasoning that they can just rely on manual snapshots. They log into the console, modify the database, set the backup retention period to 0, and hit save. The console immediately throws a hard error. AWS physically refuses to let them disable the automated backups. Why?
Because that specific RDS instance has a read replica attached to it.
I need you to explain the underlying causality there. Why does a read replica, which is just a secondary database used for serving read queries, care if the primary master database has backups enabled? How are those two systems linked?
A read replica is not just a static independent copy of the database. To function, it must be continuously updated with every single transaction that occurs on the primary database. It does this by reading the transaction logs, specifically the bin logs in MySQL or PostgreSQL. AWS RDS relies entirely on the automated backup infrastructure to manage, retain, and sequence those transaction logs so they can be reliably streamed across the network to the replica. If you set the backup retention period to 0, you are instructing AWS to destroy the transaction logs. If the logs are destroyed, the replication engine breaks and the replica falls permanently out of sync. Therefore, to protect the integrity of the architecture, AWS explicitly prevents you from disabling automated backups on the primary instance as long as a read replica exists.
It is all interconnected. You pull a tiny thread over here to save $50 on storage costs, and you inadvertently break a massive replication engine over there.
And that is the true overarching value of studying these architectural scenarios deeply. It forces you to look past the surface-level features of a service and understand the underlying mechanical physics of how the cloud actually operates.
We have covered an incredible, sprawling landscape of architecture today. Let's distill the core CloudOps philosophy we've extracted from these scenarios. Number 1, you must ruthlessly eradicate custom operational scripts. Stop writing fragile loops to patch servers or push configurations. Leverage the native identity-based polling architecture of Systems Manager. Number 2, you must enforce governance from the top down. Stop trying to micromanage hundreds of IAM users across dozens of accounts. Build impenetrable mathematical guardrails using AWS organizations and service control policies.
Number 3, You must completely abandon the legacy posture of polling for failures and embrace event-driven self-healing. Don't write cron jobs to ask if a server is broken. Configure EventBridge to instantly react to state changes and trigger native remediation runbooks. Number 4. You must intimately understand the physics of your network traffic. Do not force an application load balancer to absorb massive layer 4 spikes when a network load balancer is mathematically required. And finally, you must deeply understand the mechanisms of data persistence. Know exactly when to deploy the log rewinding magic of Aurora Backtrack versus standard point-in-time recovery, and fully grasp the extreme cost and complexity required to achieve a true zero RPO active disaster recovery architecture.
Mastering these fundamental concepts is not just about memorizing answers to pass the SOA-C03 exam. It is about building the mental models required to excel in the high-stakes, real-world crucible of cloud architecture.
But as we close, I think it is critical to look forward and consider the logical, philosophical extreme of the architectures we've discussed today.
Let's explore that.
We spent significant time detailing how to use EventBridge to trigger automated surgical remediations the instant a human makes a mistake. An engineer accidentally exposes SSH to the world, AWS config detects it, and a systems manager runbook instantly closes the port before anyone is even notified. It is a brilliant self-healing mechanism. But think about the trajectory of this discipline. As we integrate more sophisticated AI and machine learning into these control planes, our CloudOps environments are becoming increasingly perfectly self-healing.
So the system isn't just reacting to known rules, it's potentially anticipating failures and re-architecting itself.
Exactly. If the environment becomes a complex, autonomous, event-driven organism, what happens to the fundamental role of the CloudOps engineer?
That is a profound shift. We are moving from being mechanics who physically turn the wrenches to becoming something entirely different. Does the role eventually shift away from managing infrastructure directly and become strictly about governing the parameters and the ethical boundaries of an autonomous system?
Precisely. Instead of writing the code that builds the servers, are we simply going to be negotiating with the automated systems that build themselves? When a complex anomaly occurs, and the AI remediates it by making a routing decision we didn't explicitly program, our job will be to act almost like cloud psychologists, analyzing the telemetry to understand why the autonomous system made the choice it did. Will the cloud certification exams of the future even bother testing our ability to provision a VPC? Or will they test our ability to write the boundary logic that tells the AI how to safely provision the VPC on its own?
It is the ultimate evolution of abstraction. We are moving further and further away from that comforting physical server rack we talked about at the very beginning. We've evolved from physically touching the blinking green lights, to writing scripts to control the lights, to building event-driven systems that manage the lights for us.
The tide of abstraction will only continue to rise, and the only way to survive and thrive as an engineer in that environment is to relentlessly question and understand the why beneath the abstraction.
And that deep understanding is exactly what we set out to extract today. Keep questioning the hive-mind solutions, keep searching for the native architectural magic, and most importantly, keep pushing the boundaries of what you understand. We will see you on the next deep dive.